Refrigerator involves heat transfer from low temperature to high temperature. Its purpose is to reduce the temperature of the body below its surrounding. It is a reverse heat pump. The second law of thermodynamics states that this is a reverse remove of heat that can occur in the presence of external heat or work. The refrigerator system involves four processes: evaporation, compression, condensation, and expansion. The purpose of this experiment is to study the performance of the vapor compression refrigeration system by calculating the unit coefficient of performance (COP). The COP is determined by the ratio of the energy usage of the compressor and the amount of useful cooling at the evaporator. The high COP value represents the high efficiency. The advantage of the vapor compression refrigerator system its capability to remove large quantity of heat with a small mass flow of the refrigerant. High efficiency, one of the most efficiency refrigeration system at the micro scale, producing high COP and the capability to achieve sub-ambient temperature without injecting additional pumping energy at the cold junction at too much to be removed.
For theory, the second law of thermodynamics dictates that heat naturally flows from a hotter region to a colder one and not the other way around, unless energy or work is expended. The cooling system operates by extracting heat from a lower temperature space and transferring it to a higher temperature space. To accomplish this heat transfer, the system requires a supply of work denoted as W. A refrigerator functions similarly to heat engines or cyclic devices. Utilizing a working fluid known as refrigerant, the refrigerant is introduced as a vapor into the compressor, where it undergoes compression to reach the condenser pressure. Passing through the condenser coils, it cools and condenses. Subsequently, the refrigerant, now at low temperature, flows through the evaporator, where it absorbs heat and undergoes evaporation. This completes the cycle as the refrigerant exits the evaporator and returns to the compressor. The coefficient of performance, COP, is defined as the ratio of useful energy, which is the heat transfer from the low temperature source to the input energy represented by the compressor's energy consumption. The COP can exceed 1 because the energy consumption of the compressor is the difference between the absorbed and emitted heat. Thus, the COP can be calculated based on the following equation. COP equals to the heat transfer from the low temperature source divided by the input energy.
So for this experiment, you use a refrigeration cycle demonstration unit R633 PA Hilton using R141B refrigerant fluid, as depicted in figure 3.3.1.
In the step of methodology, we must identify the following components such as evaporator, condenser, compressor, expansion valve, watt meter, water flow in and out of the flow R141B. After we determine the apparatus, second step is the valve are open as the figure in 3.3.4. After the valve is open, the main switch is switched on. The coolant system is allowed to be stable approximately in 10 minutes, and the parameter listed in table 3.3.1 is recorded. The experiment is repeated by changing the flow rate of the water to the condenser in between 35 to 40 grams per second. The step is repeated 4 times. After the experiment is done, make sure the device is closed following this procedure. First, the main switch is switched off. Second, the water supply pipes are turned off in 1 minute. Third, the valves are closed to the shutdown position as depicted in figure 3.3.5 after 1 minute. This is the result that we get from our experiment. Firstly, we have the absolute condenser flow rate, condenser gas pressure, absolute evaporator flow rate, evaporator gauge pressure, and compressor power input. All of this we get from our experiment that we read from the apparatus. The result we also get from our experiment immediately. This result we get from the formula that we are discussing in question 1 at part discussion. So for the rate of heat transfer at evaporator, we're using the equation number 5. The rate of heat transfer of condenser, we're using the equation number 6. For the equation of the performance, COP, we're using the equation number 4.
So for the discussion, we need to calculate the rate of heat transfer that occurs in evaporator and the condenser for the 5 test run and discuss the results. The second is explain the effects of changing the condenser flow rate on the compressor power. Draw the graph and discuss the result obtained. Discussion 1. In evaporators, heat transfer occurs through the process of evaporation. This is when a liquid is converted into a gas, absorbing heat energy in the process. The heat energy causes the molecule in the liquid to become more energetic and break away from each other, forming a gas. This transfer of heat from liquid to gas is what causes the liquid to evaporate. The heat transfer to the evaporator will be the heat transferred from the flowing water to the evaporator. Assuming no heat loss from the evaporator, the formula to calculate the rate of heat transfer at the evaporator will be shown as below. So the rate of heat transfer at evaporator is equal to the mass flow rate of water or evaporator times the specific heat capacity of water times the temperature 1 minus temperature 2. The mass flow rate of the water at the evaporator will be the absolute evaporator in kilowatt. So next, the condenser cools the high pressure gas, releasing its heat into the environment and causes the refrigerator to condense into high pressure liquid, as depicted in equation 6. So the condenser then transfers the heat to the flowing water around it. So assuming that no heat is absorbed by the condenser, the heat transfer at the condenser will be the heat gained by the water from the condenser. The formula to calculate the rate of heat transfer at the condenser will be shown as below. The mass flow rate of water at the condenser will also be the absolute condenser in kilowatt. So the rate of heat transfer at the condenser is equal to mass flow rate of water condenser times the specific heat for water times the temperature taken in this primer, which are temperature 3 and minus temperature 4. So the calculated data was shown as in table 1 as in the results. The rate of heat transfer at the evaporator in kilowatt for test 1, test 2, test 3, test 4 and test 5 is 0.314025, 0.3454, 0.4396, 0.66992 and 0.9421 kilowatt respectively. The same for rate of heat transfer at the condenser in kilowatt. After it's calculated it is shown that we gain negative 0.4082, negative 0.5359, negative 0.4336, negative 3098 and negative 1005. So for the coefficient performance or COP, we also found that we respectively this is increased as shown in the table below. It is 1.3653, 1.5150, 1.9367, 2.9127 and 4.0088. So we use the formula or the equation 6 for the rate of heat transfer of evaporator and equation 7 for rate of heat transfer at the condenser. For the COP, we use the formula or equation 5 as shown in theory. Discussion 2. According to the calculation results tabulated in table 1, the magnitude of rate of heat transfer at the evaporator is much higher compared to the rate of heat transfer at the condenser. The evaporator absorbs heat from its surroundings, causing the refrigerant to undergo a phase change from liquid to vapor. This phase change requires a significant amount of energy, known as latent heat of vaporization, which contributes to the high rate of heat transfer at the evaporator. In contrast, the condenser releases heat to the surrounding as the refrigerant condenses back into a liquid, which typically has a lower magnitude compared to the latent heat transfer. Next, the evaporator operates at a lower temperature than the surrounding space it is cooling. This temperature difference enhances the heat transfer rate as heat naturally flows from the higher temperature regions to lower temperature regions. The graph is shown as below for plot temperature versus condenser flow rate. On the other hand, the condenser operates at a higher temperature than its surroundings, and while heat transfer still occurs due to the temperature difference, it is generally at a lower rate compared to the evaporator. The graph is shown as below for compressor power input in watt versus absolute condenser flow rate in gram per second.
In conclusion, this experiment aims to determine the coefficient of performance (COP) for Vapour compressor cooling system. The value of COP when mass flow rate of water and condenser at 25, 20, 15, 10 and 5 grams per second are 1.3653, 1.5150, 1.9367, 2.9127 and 4.0088 respectively. According to the experiment results, the COP of the Vapour compressor cooling system is directly proportional to the mass flow rate of water at condenser. At the same time, when the mass flow rate of water at condenser increase, the compressor power input also increase. However, the overall temperature of Vapour compressor cooling system increases as the mass flow rate of water at condenser decrease.
Safety procedure 1. Personal protective equipment or PPE. All personnel entering the lab must wear appropriate PPE, including safety goggles, lab coats, and closed-toe shoes at all times. The second is equipment inspection. Conduct a visual inspection for all components, including the evaporator, condenser, compressors, expansion valve, watt meter, and water supply pipes, to ensure that they are in good condition and free from damage. 3. Electrical safety. Ensure that all the electrical connections are secure and insulated to prevent electric shocks or fires. 4. Heat safety. Be mindful of hot surface, particularly around the condenser and compressor, and use heat-resistant gloves and barriers when necessary. And lastly, 5. Shutdown procedure. Turn off the main switch to power down the Vapour system. Close the water supply pipes gradually to prevent sudden pressure changes, and close all valves to the shutdown position as depicted in figure T.3.5 in methodology following the specified sequence.
This is the reference that we are using for this experiment. Thank you for listening our video.